Okay, this is 2022, Set 2, AP Physics C Mechanics, number 2. And this one has to do with collisions, springs, basically that's mostly it. Collisions and springs is what we got going on here. So we're going to start out with the very beginning of this, which says block 1 is a mass that's held at rest while compressing an ideal spring. Okay, awesome, ideal spring, and amount delta x. The spring constant of the spring is K. Block 2 has a mass M2 that is smaller than M1, and they draw them smaller, so that's nice so we can remember that. At time t equals 0, block 1 is released. At time tc, the spring is no longer compressed, and block 1 immediately collides with and sticks to, so sticks to block 2. The blocks stick together and the two-block system moves with a constant speed v as shown above, and frictional effects are negligible. Alright, now this is a little confusing. I read this through twice to make sure I understood what they were asking. The impulse on block 1, given from the interval from 0 to time where they collide, is Js. The impulse on block 1 from block 2 during the collision is J2. Which of the following expression compares Js and J2? Okay, so originally block 1 has the spring on it, and the spring pushes it. And impulse is the integral of force with respect to time. It's also F delta t if we had a constant force. Now I know a spring force is not constant, okay? But we know that that also gives us a mass times a change in velocity. So we're going to tell this is equal to, we're going to call it V final, and it started out at 0, so we're going to get M V final. So that is Js. Oops, okay. So Js is MV final. Alright, but when it collides with block 2, it's going to end up, so J2 is going to be that M, and this is M1. It's going to be that M1 times its V final there minus what we had here, which is, I'm going to call that a V final from this one. Maybe I should call it V1, but we're just going to pretend that this V final goes right there. Okay, but we're going to end up at a V final that's less than that, but not 0. Okay, so we're going to get a V, we're going to call it a V prime final. Okay, that V prime final is not 0. So this difference right here is smaller than that difference, or that difference, because I'm changing from V final to a smaller, or well, the V final that I had before to a smaller velocity, but here I went from 0 to that V final, so I'm doing a smaller change here. So because of that, J2 is less than Js, so that's this one. Js is greater than J2. Okay, and that's because delta V is smaller from the collision with block 2 than the delta V from the spring. Okay, because the spring gives it more of a change in velocity than that collision does, and so therefore the collision, or the, excuse me, the impulse is smaller for that situation. Okay, now on the following axes, draw the magnitude and the momentum of each block as a function of time before and after the collision. The collision occurs at a negligible amount of time t, and the grid lines are shown on the same scale. Okay, so block T, the second one, block 2, he's doing nothing up to the collision, right? And then after the collision, he has a magnitude of mv. Okay, so I can draw him without even thinking. That's pretty easy to do. Okay, so I'm just going to draw him no momentum. Now he has some momentum, but it's constant both times. Constant 0, constant whatever they're doing afterward. Block 1, however, okay, afterward, he's going to have momentum. Before he's going to have momentum, though. But before, his momentum goes up, and it goes up big at first, and then not as much, not as much, not as much until I get here. That's the spring, because what happens is the spring is moving. The spring is pushing really hard at the beginning, so it's changing its momentum fast. But then as we go along, the spring pushes less and less because it's compressed less and less, so we get a lesser change. So the change in momentum, which is the slope, gets smaller and smaller and smaller. But once I hit that collision, I go from having this to boom, I have a smaller amount of momentum. And this block is going to drop down to a constant momentum. Now his momentum will be higher than this one because he's bigger than this one. This is a smaller block, smaller momentum. Bigger block, bigger momentum. Same velocity, but the difference is one is bigger, so it has a bigger momentum. All right. Part C, and I love when they do this to us. Show that the velocity of the two block system after the collision is given by this equation. So I kind of know where I got to be. I like to know where I've got to be. So let's see. Okay, first of all, I have a collision. So I've got block 1, movement at V1 initial, block 2, movement at V2 initial. They collide. I've got block 1 plus block 2 moving at a V final. Now I know in the beginning this is 0, so this term falls out. So M1 V1 naught, and this is solved for V final, divided by M1 plus M2 is equal to V final. So I'm almost there. Like I'm really close to looking like that equation, but I've got a K in there, so I must have something to do with the spring. Okay, so let's go back to investigate the spring thing. And so the block 1 gets energy from the spring. Okay, now you can do this with work too. You do work of the spring is equal to change in kinetic energy of the block. But I like energy because energy is kind of my go-to if I can use it. So U naught plus K naught equals U final plus K final. But who has that potential energy? That's the spring. Okay, this is 0. We have none. Okay, in the end, we have none because the spring is relaxed. And this kinetic final is the block. So I can set the spring's potential energy, which is 1/2 kx squared, is equal to the kinetic energy of the block, which is 1/2 mv squared. Okay, and we're going to call this V1 naught. Okay, because that's what we got it in over here as is V1 naught. All right, so I've got a half here and a half here, so I can take that away. So V1 naught is going to equal, I'm going to divide both sides by M1, and then I'm going to take the square root. So I'm going to get the square root of K delta x squared over M1. And I changed that to delta. Yes, I did, because in their equation they have delta x, so I'm just going to put that in there. Okay, so I'm going to put that in here. So I've got M1 times the square root of K delta x1, or delta x squared, excuse me, over M1 all over M1 plus M2 is equal to V final. In theory, I think we could probably stop here. But if we want to clean it up to look exactly like theirs does, there's a couple of things I can do. The first one is this M1 can go under the radical, but he can only go under the radical if he goes under as M1 squared. Now, let's go up here and finish off. So V final is going to equal, the delta x can come out because he's squared. The M1 squared and M1 on the bottom, I can get rid of one of those. So I get the square root of K M1, okay, and that delta x came out, which they've got it out here at the end, so I'm going to put it there, over M1 plus M2. And there I am at the place that they wanted me to get to. I look identical to their thing. I don't know that it would be wrong to stop here. I think we're there. You know, it's just a little bit of algebra to simplify. So, but that's what they wanted, so here we are. Okay. Now we're going to change it up a little bit. A group of students this time uses the setup to perform an experiment, and they measure the mass of block 1 to be, so they give me a mass, and the spring constant K is this. They give me a spring constant. The mass of block 2 is unknown, and they perform several trials, and in each trial the spring is compressed to different delta x, and the final velocity V is measured, and the graph velocity as a function of time is shown. Draw a line that best fits the data points shown. All right, that's simple enough. Usually we're at the point. Put my ruler on here as best I can. And draw me a line. Okay, that looks like a pretty good line. I hit most of the points. Got one slightly below and slightly above, but everybody else is kind of on the line. All right, using the best fit line. Oh, using the best fit line. I'm probably going to calculate a slope. I'm either going to do a slope or area, but if they say using the best fit line, it's usually slopes. So I'm going to go back, and they want me to calculate the mass of block 2. So I'm going to go back to what I did just a second ago to this equation. And I'm going to back up to right here, I think. Maybe. No. We'll just start here. We'll start with what they gave me. So they gave me that velocity is the square root of k m1 over m1 plus m2 delta x. Okay, I want m2. So because of that, I'm going to put m2 over here. So I'm going to do m1 plus m2 times v is equal to the square root of k m1 delta x. Okay, I can see that my slope is going to be v over delta x. So I'm going to put v and delta x together. So I'm going to get m1 plus m2 is equal to the square root of k m1 delta x over v. And then m2 is going to be the square root of k m1 delta x over v minus m1. Because I'm going to subtract my m1 from both sides. Now, at this point, you might be going, oh my goodness, what's she got going on here? But I can plug in. They've got stuff I can plug in. What's k? 150. What's m1? 0.5. What's this? That's my slope upside down, so 1 over the slope minus m1 is 0.5. So I could find m2 right here if only I knew the slope. So let's go back to our graph and let's see if we can figure out the slope. Okay, I'm going to look for intersections if at all possible. I don't know that I'm going to have any. So in this case, I may use data points. I try to steer clear of that, but if your data points are on the line, we can kind of estimate. This would be 0.0225 and 0.25. And this one would be 0.01, and I'm going to guess is 0.125. Okay, so my slope is going to be 0.25 minus 0.125 all over 0.0225 minus 0.01. So let's see what that gives me. So 0.25 minus 0.125 divided by 0.0225 minus 0.01. And my calculator says that slope is 10. So I'm going to put that in here. So this is 150 times 0.5 under the radical times a slope of 10, so 1 over 10 minus 0.5. So let's see what that gives me. So the square root of 150 times 0.5 divided by 10 minus 0.5. All right, and I get 0.37 kilograms. Make sure you put your units on that. Okay, I looked at this. This was an accepted value between 0.27 and 0.37. So I'm within the accepted value. So we're okay with that. And that is an accepted value for the mass of our block 2. Okay, last thing. After the experiment, the students used a balance to measure the mass of block 2 and found it to be greater than what they found in part D. So to explain this discrepancy, one of them says, hey, the spring constant must have been bigger. Maybe well, not must have been bigger, it must have been different. Okay, and then so they said, you know what, we're going to measure the spring constant again and find it. So what do we expect it to be? Is it going to be greater than, less than, or equal to 150? Okay, so I'm going to go back and I'm going to write that equation. M2 is equal to the square root of k m1 times 1 over the slope minus m1. Okay, now we know the slope of my line stays the same because that's my data. That's what I just graphed. That's not changing. Okay, m1 is the same. So that stays the same. So the only thing that can change is that. That's the only thing that's going to make a difference to this mass. And they said the mass is larger. Okay? To get a larger mass, the right side must be larger. And the only thing that can change is that K. So K must be larger. So our K prime must be larger than what we originally thought that our K value was. Because if it wasn't, we wouldn't get that bigger number.